Hi, today I want to start a series of algorithmic courses that is based on an MIT course that's called The Introduction of Algorithm, and also CLRS book and other problems that I can find them in the online resources. It's like an introduction, and first of all, we want to explore the core computer science concepts, problems, algorithms, and the importance of efficiency. First of all, what is the problem in computer science? A problem in computer science is like a mapping. It's a mapping between two subsets, input and output. The input, it's what we start with them, the starting data. And output is the desired result, what we want to achieve. And the problem is something like a mapping, something like a solution that connects its input to the desired output. How it happens, especially in computer science, it happens by algorithm. Algorithm is like a process, like a method you can that solve the problem, and you can consider it as input output function. What it means, it is like a function that you gave it the input, and you will give you the corresponds output, and it's like a guidance of a solution that you have a step by step. In each step you know what you must do to have a solution, and at least you can have the correct result. Why this method is correct? The correctness of algorithm based on a mathematical concept. This mathematical concept is called induction. What's induction? It's a mathematical concept. It has 3 steps. First of all, I will give you summary because I think maybe all of you don't be familiar with this mathematical concept. First of all, you try to understand that what happens if you have just 1 or 2 data. If you have a formula, if you have a desired output, in 1 or 2 output, you try to find that, or you prove that okay, it's correct. If you don't have a desired output in 1 or 2 or 3 output, you try to guess in 1, 2 or 3 input, you try to guess what will be our output. We call this step as base case, and then we will assume what will be correct output for example, K input, and we call it the inductive hypothesis. And in step 3, we try to prove the desired output for K plus 1 input, and we call it the inductive step. If you are not familiar with this induction, with this mathematical concept, I give you a so easy example. It will help you to understand it better. We have a famous formula in mathematics, and it's like this: the sum of 1 until n, we have n numbers, 1 until n, the sum of them is equal n multiple n plus 1 divided by 2. Now you want to prove it, and you can use induction. By induction method you can prove it so easily. First of all, we have the base case. In base case, we must examine that for one input or two input the formula holds or not. Just consider that k is equal 1. Then the left side of the formula will be 1, and the right side of formula will be 1 multiple 2 divided by 2. You can see it's obvious that the formula, the equality holds. So the base case happen. You can see that for one input it holds. If you want, you can also check it for k is equal to. Then in your left side we'll have the sum of 1 and 2 that become 3 in the left side. And in the right side you will have 2 multiple 2 plus 1, that is 3, divided by 2. Again you have 3. So the left side and right side are equal, means that the equality holds. So the base case happen. When the base case happen, when you guess your output result, then you go to the next step, inductive hypothesis. What it means? It means that you assume that this formula holds for k input. Means that you assume that the sum of 1 until k is equal k multiple k plus 1 divided by 2. Now when you have the inductive hypothesis, you go to the step 3. In the step 3, that is called inductive step, you try to prove the equality holds for n equal k plus 1. If you can prove that the equality holds for n equal k plus 1, means that it holds for k plus 1 input, then you generalize your inductive hypothesis, means that this formula is always correct. And it's so easy. You must just show that the sum of number between 1 and k plus 1 is equal to the right side. Just write 1 sum until k plus k plus 1. Okay, the sum of 1 until k is, by the inductive hypothesis, k multiple k plus 1 divided by 2. And now so easily you must sum these two numbers. If you sum them, you can easily find that it will be equal k plus 1 multiple k plus 2 divided by 2. That means that you show that the equality holds for k plus 1 input, and it means that you proves this equality in a general form. The correctness of algorithms are also like this. They based on the induction. After the correctness of algorithm, It's important that we understand how much they are efficient. Okay, they are correct, but how much they are fast, how much they are have a good performance. We don't count the time, we don't measure the time for this. Why? Because of different hardware performance, so it can not be a good way to find how much an algorithm is efficient. What we do, we focus on the operation. We find, for example, for algorithm, we have different steps: step 1, step 2, step 3, and we have n input, and by considering the operation in each step and find how much they related to get to each other. For example, you can have a loop in step 1, and in step 2 you have just a sum operation. By considering this operation and their relation, you can find a function for the counting the operation, and this function has the number of your input as a variable, and then you try to understand how much this function f grows rapidly when your input increases. Means that when we increase the input size, how will act our operation function f. And to understand it, we focus on dominant term. We have for solution a problem different algorithms. It's like climbing a mountain, step by step, and it's so important to know that which way is better, is an efficient. And to understand this efficiency, we have different criterion. I mean that we have different things to understand the differences between operation function. One of this notation is the big O. The big O is like a upper bound. It means that when we say that, it shows the maximum growth rate. It said that Fn is equal to OGN. It means that the Fn always stays behind the Gn. Means if we have the diagram of F and G, it's like this. It will be G, for example, and it will be F. As you can see, when the input size grows, when we increases the input size, you can never see that F grows over G, grows more than G. So G is a lot. It's always beyond the G, and G is like a upper bound for the F. And when F and G be operation function, that you can see in the worst case, the complexity will be G. For famous growth type that you can see in many cases, we have a table, and in this table you can understand how they behave, and by this table you can understand how much your algorithm is fast. One of the first growth type is the constant type, and we show it by O1. It's the fastest. Means that it's independent of input size. How much you want to increase your input size, it will not change the complexity of my algorithm. The second is logarithmic. It's also very efficient and very good because of the logarithmic function behavior. And then we have the linear function. The linear function uh, grows completely proportional with inputs. And we have the linearithmic. The linearithmic that is n log n is, you can see many of sorting algorithms with this complexity. And also we have polynomial, then you can see that their growth rate is so much much more than the linearithmic or the linear. And also exponential, that is extremely fast growth. And at the worst case we have the factorial, that their growth rate is so dramatically bad. I mean that they grow so fast and really not a good algorithm. They are not a good algorithm, so has a lot of complexity. If you want to understand better the complexity of algorithm, we have excuse me, we have different notation. More than the upper bound, we have theta and omega notation. Theta notation express exact the growth rate, and it shows that two functions grows at the same rate. The growth rate are the same. For example, we have two functions. Fn is 5 multiple squared n, and gn is 20 multiple squared n. Fn and gn has same growth rate. If you consider, for example, n equal 1, then f will be 5 and g will be 20. Of course, g is more than f, than f. But if you consider n as, for example, 10,000, then you can see that f and g are so much the same. Their growth rate are so much the same. Why it happened? You can see that their differences, both of them are squared, and their differences is just this coefficient. And this tiny coefficient, when n goes to infinity, this tiny coefficient will not change their behavior so much. Just you can see their diagram. For example, for g, it will be like this. And f will be like this. You can see g and f are so much the same. Why? Because both of them are exponential, and their exponent, both of them are squared n, and only the differences is the coefficient. It will not change their behavior when the input size grows so much. So we can say that Fn is equal to theta Gn, means that they have the same growth rate. And we have the omega. Omega is like an upper bound. It means that, for example, if f is like this, g will be like this. It's like a lower bound, means that g is always a better performance than f. And by theta, omega, and O, we have upper bound, lower bound, and same rate, and you can really understand how much your algorithm will have a good performance. You can you can always think about the operation function of your algorithm, and then you can have, as I've said, you can have some famous operation function, and then by using this lower bound, upper bound, and the same growth rate, you can guess, okay, what will be my algorithm behavior. For example, we always have that for a logarithmic function. We have a diagram like this. It will be the logarithmic one, and n will be the linear one, and s squared n will be like this. That you can see that the logarithm n is like a lower bound for the linear operation function, and s squared n is like a upper bound for a linear function. And you can see that how much their performance are different. Now, to understand better the algorithm growth rate, I give you here a list. At the top of the list, we have the less of growth rate. The less of growth rate, and here we will have the most growth rate. Means that when I give you this list, the growth rate of this function increases. So first of all, we have the constant time. As I said, it remains stable regardless of input size. So this growth rate is 0, and it's the least one. Then we have the logarithmic. It grows so slowly, as I said. It's such a good, it has a good performance because of the logarithmic function. We know that the logarithmic function diagram is like that. So when you increase the size of input dramatically, you can see that the logarithmic function increase so slow. It means that your algorithm has a better performance. And then we have the linear time. The linear time increase as the input size increase. They have growth the same. And then we have the linearithmic time that I've said it's faster. The growth rate, I said the growth rate is faster than linear time, but it's also good. You can have this complexity in sorting algorithm. And then as a upper bound, we have the polynomial time. This polynomial time increase as the power of input size increases. And then we have the worst cases, that exponential time and also the factorial time. So as I've said, the growth rate in this direction increases. You must always know that when the growth rate increases, means that the complexity increases. When the complexity increases, means that the efficiency of your algorithm decreases, and it means that the speed of your algorithm decreases. So the best algorithm performance is here, and the least algorithm performance is here. In many cases, they are not approvable, and you can have here a better performance. Especially if you want to do programming in competitive programming. I mean that in some cases, when you have, for example, a squared n, we call it a brute force solution. Means that it's too complex, it takes too time, and you cannot achieve the accept for the judge system. It's like the first solution for you, and then you must think about how I can decrease the complexity of my algorithm. Because as I gave you this diagram, the S squared n is like this, and it isn't a good performance. You must try to become near a linearity and logarithmic performance. For the last slide of this course, this session, I give you an example. In this example, we have different functions, and we want to understand the slowest until the fastest growth rate. I say again, fastest growth rate. How much? Which one has the fastest growth rate? You have in the slides before, you can find it here. We have this one. We have the famous function, and then we have here the list of them, how much they are, their growth rate is faster. And now to solve this problem, you can use exactly this list. First of all, you have a polylogarithmic. It's a logarithmic, it's log n, and it has a power. This power is just a number, and it will not change the performance of logarithmic function so much. So you can see that it will be the best performance. It will have the best performance. Also, as you can again see in the list, the linearithmic time has a better performance than polynomial time. And here, the n with power 2019 is a polynomial. And as we had in the list, so the linearithmic has a better performance. It's also obvious. Again, you have the another n squared and log n is another polynomial. And here we have an exponential. As you can see, this exponential time growth rate is more than polynomial time. So it means that it's obvious that the O(n) squared n log n is less than O 2019 with power n. Just this one rest for you. If you want to prove it, it's so easy. No, you have no problem. Just consider you must find the limitation of n with power 2019 and the limitation of s squared n log n, and find this both limitation when n goes to infinity. If you find this asymptotic performance of these two functions, you can find that, okay, it will be like this, and by this you can prove that this relation holds. And then we have this final order, as you can see here. In the next step, I will go to the data structure and I will try